You are the lead electrical engineer assigned to a massive new offshore oil platform. You are staring at a blank slate. Your facility will be isolated by hundreds of miles of open ocean, battered by severe weather, and entirely responsible for generating its own electricity. Before you can specify a single length of copper cable, order a transformer, or size your switchgear, you have to answer one exact question. How much electrical load does this entire facility actually need? If you underestimate that number, the system will suffer severe voltage dips the moment large pumps turn on, causing the plant to trip and go dark during critical black start operations. On the other hand, if you overestimate the load, you will waste millions of dollars purchasing oversized gas turbines. Worse, those oversized turbines will be forced to run at partial capacity, resulting in extremely poor thermal efficiency and massive fuel waste. To solve this problem, you have to apply a rigorous mathematical workflow. You must calculate the total plant peak load, or TPPL, and then use those figures to size your generators according to what the industry calls the N-1 philosophy. Load estimation is the foundational mathematical model that dictates the physical footprint, the capital cost, and the ultimate viability of the project. The calculation process begins by taking thousands of disparate mechanical components, pumps, compressors, lighting circuits, and heaters, and organizing them into a strict two-dimensional classification matrix. This diagram represents that matrix. The y-axis tracks our first dimension, criticality. We divide every piece of equipment into 3 operational tiers: vital, essential, and non-essential. We categorize vital loads as anything required for life safety and damage prevention, like UPS systems, fire and gas detection, and emergency lighting. Essential loads are those that would cause a degradation of the production process if lost, such as main gas compressors. Finally, non-essential loads include systems like standard HVAC, where a temporary loss of power has no immediate operational effect. The x-axis introduces the second dimension, duty category. We classify the operational state of these loads as continuous, intermittent, or standby. We map the equipment this way because a vital load that sits almost entirely on standby, like a diesel fire pump, requires a completely different power reserve calculation than an essential load that runs continuously, like a glycol circulation pump. Once every load is mapped, we face a physical reality of industrial power systems. All of that equipment will rarely, if ever, operate simultaneously at its maximum nameplate rating. To account for this, we use this bar chart to demonstrate diversity factors, represented as DC, DI, and DS. These are mathematical multipliers used to scale down the theoretical sum of all connected loads into a realistic operational demand. Watch how the multiplier changes as the project matures. During front-end engineering design, an intermittent load might get a conservative 0.6 factor. As we move into detailed design and receive firm purchase orders with actual manufacturer data, that factor drops to 0.3, precisely shrinking our actual load calculation. We synthesize these classifications and multipliers into the total plant peak load, or TPPL formula. As you see here, we sum the continuous, intermittent, and standby loads, each modified by its specific diversity factor. If we calculate the demand for a single process switchboard, we replace those variables with real kilowatt values. A continuous load of 1,013 kilowatts multiplied by a factor of 1.0, plus 320 kilowatts of intermittent load at 0.5, and 633 kilowatts of standby load at 0.1, resolves to an actual peak demand of 1,236 kilowatts for that specific board. Even with this precision, engineers typically add a 10 to 25% margin to that final TPPL figure, specifically to accommodate future plant expansion, as oil and gas reservoirs behave unexpectedly. Calculating the TPPL strips away the paranoid assumption that every motor and light will run at exactly the same time, preventing massive capital waste while maintaining strict safety margins. With the TPPL established, we transition to sizing the physical power generation. Because offshore grids operate in total isolation, they cannot draw emergency power from a mainland utility. This diagram outlines the N-1 philosophy. Here, N equals 5 total generators. N-1 dictates that the plant's generation must be sized so the facility can run fully loaded even when one generator is taken completely offline for maintenance. For the 4 active generators, we calculate the initial load factor. As the gauges show, these running turbines must operate between 70 and 85% of their rated capacity to achieve optimal thermal efficiency. The true test of the system is an unexpected trip. Watch what happens when one of those 4 active generators suddenly fails, dropping the isolated grid into an N2 state. The remaining 3 turbines must instantly absorb a massive spike in demand. We call this the post-disturbance overload factor. The gauges immediately spike into the red, but they must be carefully sized so they do not exceed a strict 125% overload threshold before the system can react. The N1 generation sizing calculation represents the razor-thin margin between a localized mechanical failure and a catastrophic platform-wide blackout. What happens if that post-disturbance overload actually exceeds the physical torque limits of the remaining turbines? This data table shows how the Power Management System, or PMS, intervenes. It relies entirely on a load-shedding priority table, ranking every industrial load on the platform sequentially from priority 1 down to 26. When the remaining generators are pushed beyond their physical limits, the PMS automatically cross-references this table and instantly trips the lowest priority items. Notice how the connected system load curve drops immediately as the bottom rows are cut. By shedding the non-essential loads, the automated system brings the generator overload factor back down below 100%, pulling the strain gauges out of the critical red zone and rescuing the system frequency. This automated survival mechanism functions properly because every single electrical load was correctly classified in that initial 2-dimensional matrix back during the first phase of design. Electrical load estimation is a continuous operational model. It dictates platform safety, dynamic system stability, and the economic viability of the project.